All right, good morning. So for anybody that's catching this later or live online, unless of course you have talked to me first, you're starting to tempt me to have in-class participation assignments because there's a grand total of 2 people in class right now. So keep that under advisement. I still expect in-person attendance, appreciate in-person attendance and engagement. And it's getting a little silly at this point. So might be increasing some in-class participation if you force my hand. All right. Aside from that, wanted to come back to Redox Chemistry. Did post your second MATLAB assignment now. I put a due date that's going to be flexible. I put it for the class period after our exam, but I am encouraging everybody to take a look at it before the exam because it's relevant course material. I think it'll be good for you to see about approaching that problem, see, okay, what does it take to do this? It's something we actually did talk about in class already. It's slightly different, but not much. So I would encourage you to try that. It's probably not too much work, I think, to just do it all together. So feel free to complete that before the exam. Or if you're just completely slammed and stressed and everything, let me know if you would like an extension on that. I'm not too concerned one way or the other for that. Okay, so that's up. I still have not posted your final total MATLAB assignment, but I'll get you that very soon, possibly later today. Like I said last class, it's going to be kind of pick your own adventure in terms of which system do you want to model and build in a program. I did not put in this current MATLAB assignment or sub-assignment, I did not put a solver type of a task at this time. I am considering coming back and doing that, but that would, if anything, be for the kind of one last step along to build into the bigger project. So, okay. So a couple logistics there out of the way. So before we pick back up where we left off last time, I wanted to take a small step back in the realm of redox chemistry to say, well, how do we know if we have a redox reaction in the first place? Like what is a redox reaction by definition? We talked a lot about that already, but how would we identify it? One good way is to see if we have a pure element on one side or the other. There's a very good chance that if we do have a pure element and it's not just like staying a pure element, then there's a redox reaction at play. Maybe we can think of a catalytic system where we have some metal that ends up being unchanged. There's a chance that we would see that same metal on both sides, probably not within the realm of what we're going to do. But even then, there's a pretty good chance you had a pair of redox reactions to catalyze it or to refresh that, to get it back to the state it was in. But in general, for most of the things we'll take a look at, if it has something like a pure element, let's say zinc here, chlorine as a Cl2 gas, that's purely chlorine, right? Cl, some amount of Cls. Those are pure elements. And then on the other side, it's a combo. That means pretty much guaranteed we have a redox reaction, meaning something changed oxidation states. So we can define a redox reaction as a reaction in which something has changed oxidation states. So in this case, zinc, metallic zinc and chlorine gas would go to zinc chloride. And if we stop and think about it for a moment, we should recognize that the Cl2s here will each have a -1, and the zinc should have a +2, very likely, whereas over here they both had zeros. Likewise, we could have a mercury oxide going to elemental mercury and elemental oxygen. In this case, would be very good. You know, we could assume this is a -2 and therefore a +2 for the mercury. And here there's no charges, so these are both 0, right? elemental. Okay, so in both those cases, we see that there are changes in at least one element, and in fact, both of those, there's two elements changing their redox or their oxidation state. We could look at similar reactions or reactions that might look a little similar that are not redox reactions. So here with magnesium oxide, we have the oxygen should have a 2 minus, magnesium should have a 2 plus. We go over here, each of the H's should have a +1 and oxygen should have a 2 minus. Over here then, the OH groups should each have a minus and the magnesium should have a 2 plus. Now, I say the OH groups should have a minus, that's kind of obvious from a hydroxide, but we could look a little deeper and say, well, really that's a combination of a -2 and a +1 comboed together gives us a -1, right? So if we put all those pieces together, we see nothing really changed oxidation state to keep everything balanced and happy. Same thing we could look at with calcium carbonate or calcite here. So this would be a 2 plus. The CO3, we've often seen that as 2 minus, so that's probably what we would first think about. But if we stop and break it down, each of the O's should have a -2, and the carbon would have a +4, I believe, or does that balance it? Yeah. So that way we have a total of +6 and a total of -6, right? So carbon is often plus or -4. Then over here we have, if nothing, if we just take a look at what we expect, the oxygen again -2, calcium 2 plus. Over here, 2 oxygens at -2, and the carbon is still at +4. So with that, we see nothing really happened. Anytime we have a combustion reaction, we expect that to be some sort of an oxidation event. In fact, if we have some, a lot of times when we think about combusting some organic carbon, we would have, some organic molecule with some carbon on it somewhere, ultimately going towards CO2 and probably water. And when we take a look at that setup, we are almost always going to end up yielding a +4 here with the carbon, or well, we are. But over here, it's going to be in a more reduced state typically. So we're going to end up going from a reduced to an oxidized situation. So a lot of times these will have hydrogens, for example, each having +1. So maybe this is going to be in a -4 state. So a lot of times the carbon over here will be in a -4, and we're adding enough oxygen to take it over to +4. You could even think about that with a pure carbon. So just carbon with some number of carbons, so diamond or fullerenes or whatever. That would be in a 0 state. We could oxidize it adding oxygen and ultimately put it into a more oxidized state, right? So in either case, we could combust it. I think that, and I've heard of some mixed stories on this, so I might have some of the details a little bit wrong, but part of the issue with Chernobyl, the reason there was some explosion there was liquid graphite was being used as a coolant, and with all the other human errors involved, you could actually combust graphite if you get it into the right temperature and everything. So there was no nuclear explosion there. There was a meltdown, but whatever explosion did happen, I think was to do with graphite combusting with the temperature. Okay, so back to the half reaction. So here's where we left off last time. We said each half reaction we can write for a given total oxidation reaction. We're going to break it into half, one species at a time. So if we're taking a look at our, let's say the zinc and chloride example here, we would take that and say, let's just do half of it, what's happening to the zinc, and then the other half, what's happening to the chlorine, and then add those together afterwards. So we're going to take and write it as the reductant going to an oxidant plus electron, and then the oxidant plus an electron going to the reductant is kind of the formulation. Once we do that, we will be able to combine them, and in fact, we'll get into this in a moment, but the convention is actually, we'll probably write them both in the same formulation and then flip one so that we subtract instead of add. It's just a matter of how we decide to write them up and describe them. So really what we'll probably do is write this as both reductant forms but then when we combine the two, we can subtract instead of add, or however we need to arrange it to get everything to sort out properly. But we'll come back to that in a moment. Point being, we can look at the system with an oxidant and a reductant reacting, causes some change in oxidation state, and therefore something is now oxidized and something else is now reduced, right? So with that, we will get the net reaction without any electrons, but we are splitting it in half so we can track those electrons and understand the system a little better. Okay, so how do we balance one of these reactions? Well, what we're going to do is it draws a lot on what we've done in the past with balancing chemical equations. It's not super different, but we have a nice set of rules that we can follow. And here's where I'm going to say for both halves, we're going to just take the same process, and then when we put them together, we're going to add or subtract however we need to and arrange them accordingly so that we balance properly. Okay, so step one is identify what's going on, right? We identify the reactants and products for each half of the reaction, so the reductants and the oxidants, and then we're going to write each with the oxidized form on the left and the reduced form on the right. We'll go through some examples so we can kind of piece this together visually and get a little practice with it. So here's where we're just going to treat them both, taking the oxidized one on the left and the reduced one on the right. So R for right. Then we're going to balance each according to the atoms excluding hydrogen and oxygen. So we're going to deal with those later. So we're going to balance, like the zinc and the chloride, for example, make sure there's the same number of zincs and the chlorides, right? So we're going to balance those, adjust anything we need to get those balanced. Then we're going to balance the oxygens next. And we can do that if we have some imbalance by adding water, okay, to one side or the other. After that, we balance the hydrogens, adding H plus to one side or the other as needed. And that gives us a systematic approach. And we kind of take this approach typically anyway when we're balancing some other system, where we'll notice that's kind of stepwise. Last, we balance by adding enough electrons. And we can check this. So electrons to balance the charge, and we can check that it is really the right amount of electrons, given that that amount of electrons should match the change in oxidation state of whatever is being oxidized, okay, or reduced. So if we had that previous example where carbon was going from a -4 state to a +4 state, that's going to require 8 electrons somewhere, right? So that overall we can see that playing out. Okay, then if we're adding 2 reactions together, we might need to multiply by some factor so that if we had 4 electrons happening in one half reaction and 8 electrons in the other, we'll need to multiply that 4 by everything in that 4 by 2, right? So that the total reaction is also matching that 8 electrons. Sometimes we'll have systems where we have a 1 electron step that ultimately gives an 8 electron total change. So if we're looking at some, I don't know, hydrogen sulfide going to sulfate, there's a lot of electrons that need to be transferred, but maybe it's 1 at a time. So there's 8 of the other half reactions that need to occur in order to do that full oxidation. In those cases, it's taking, let's say, in that example, 8 peroxides or something. And so there will be 8 on that side to get the 8 electrons required to satisfy the total. So that's what we're saying here. Sometimes we'll need to account for how many total electrons did we need. Okay, and then finally, we're going to combine the two half reactions back in such a way that gets rid of the electron terms. And here's where we might need to flip or subtract instead so that we can mix them properly, right? And you can imagine we can add reactions if the electrons are on opposing sides, or we can subtract if they're on the same side. And either way, algebraically, it will come out. But the convention, again, is to take the oxidized forms on the left, reduced forms on the right, and go from there. Okay, so we'll do some flipping back and forth here. And we'll take a look at a couple examples. First being ferrous iron with 2 different oxidants. We have dissolved ionic iron exists in anoxic groundwater as the reduced species Fe2+. When such water is used from drinking water supplies and is brought up to the surface and exposed to the atmosphere, Fe2+ is oxidized by O2 to get to Fe3, so ferric iron, which is insoluble, as we've learned, at neutral pH and precipitates as these iron hydroxides. Hypochlorous acid, so bleach, HOCl, is a common disinfectant, also oxidizes Fe2+ very rapidly to Fe3. And so the challenge here is to write a balanced reaction. We're going to start with oxygen as the oxidant. We'll do the hypochlorous acid next. So that's the first step, is to try as oxygen. Interestingly, just yesterday I was emailing with Brian Peters in Nicaragua. He's a guy we've worked with last semester doing some water quality stuff, and he had sent me a water quality report just asking for like some perspective. They had some groundwater in a new well, pulled it up, and I was kind of taking a look at the stuff, and he was kind of surprised it had a lot of turbidity, which for groundwater that's a little unusual because the natural filtration should remove a lot of particles. It was also high in iron and aluminum, kind of above the typical thresholds that were allowable. And you know, he was thinking at first that, like, well, maybe the plumbing wasn't cleaned properly, maybe there's some debris left or something, and after all the drilling and installation of the pipes, yeah, it makes sense if you had some particles, especially from the piping and stuff, maybe that's adding some metals. And I was thinking about it, and I was like, well, this is good timing because we were just talking about all these precipitates and everything. If there is a lot of iron, once you pull it up, it might be coming out clear and non-turbid, like looks pretty good, but then as it equilibrates with air, becomes oxidized, we might get some Fe3+, and then forming these precipitates, right? So that's ultimately what right now my best guess is that might just be happening, and it just maybe a function of how much iron and aluminum are in there, because aluminum will do something quite similar. Okay, anyway, putting the aside, let's take a look. So let's do this oxygen as an oxidant. So take a couple minutes, think about how you're going to approach this. What are those half reactions? And we'll walk through it together. So I'm just kind of writing up effectively what the total reaction kind of looks like. And I'm not balancing this part yet. So one of the first things to kind of notice is we've got two species undergoing some sort of reaction, right? It's iron. And so the iron species, if we put the most oxidized form of iron in the solution, that should be the Fe3 version, which is the FeOH3s on the left. So that's the oxidized version on the left, and the reduced version on the right is the Fe2+. Now I'm not adding everything else in yet and balancing everything yet, but that's kind of a starting point. And we can do the same with oxygen, right? So if the O2 is the oxidized version of oxygen in the system, water should be the reduced form. Okay, so we're not going to use that Fe term that also has some oxygen in it. We're going to just take oxygen with respect to the water. Okay. So take a couple moments to work through those, see if you can, I'll flip back to the steps for a second so you can kind of see where you might have left off, right? So we're going to balance based on atoms that are not H and O. I guess for the oxygen one, we kind of have to do that one. Then balance for oxygen, add water as needed, then balance hydrogen, adding H plus as needed. Next, add the charge. Okay. So we'll do, I'll write this out, we'll say it. Add anything but H and O, then O, then H, then E. Now, let's see. Let's put here. Bless you. How are you feeling about that? Feeling okay? All right, so it should probably be looking something like this, where we have, for the iron, we'll just keep one iron on both sides for now, and then we balance the oxygen, so we need 3 waters on the right to match the 3 OHs here. That gives us with 3 extra H pluses, so we put 3 H plus on the left to get that balanced. And we should have at this spot FeOH3 plus 3H plus is in equilibrium with Fe2 plus 3 waters. So last we need to balance the charges and use electrons for that. So I left a little space for myself in this line, but not on the page. So here we would then add enough electrons on the side with the most positive charge in order to get equal charges on either side. So here we have 3 plus on the left and 2 plus on the right, so we'll add 1 electron on the left, plus E minus, gives us a total of 2 on the left and 2 on the right. So another thing we can stop and think about here is we can check how much did the oxidation state of the iron change. It went from 2 plus to 3 plus, right? So it changed by 1. We've added 1 electron. That's a good match, right? We have some more confidence on that. I think step number 6 is to double check that we balance everything properly and to double check that, essentially. If we flip back. Yeah, double check. Okay. For oxygen, we take the similar process, O2 in equilibrium with water, and we balance the oxygen, so we need 2 waters. And to balance the protons, we need 4 H plus on the left, and that kind of obviously we'll need 4 electrons as well. Just make a little more room. Just do this. Okay, and we can check the change in oxidation state. Oxygen on the left is 0 state because we've got pure elemental oxygen, and on the right, H2O, each H should be a +1, the oxygen should be a -2, so it's a net change of 2, and 2 of them are changing, so we can divide that 4 electrons that we added by 2 and to get our net change of 2 per oxygen. So all that should balance out, and we'll double check that we did that properly with the book's solution here. So we start with iron. That's here, and then move on to oxygen in a moment. So we have that 1 electron change, adding the 3 waters to the right, adding the 3 H plus to the left, adding the 1 electron accordingly, and everything's balanced. We can write that, if we want to, as a net Fe3 plus an electron goes to Fe2, right? That's not doing anything stoichiometric or anything like that. We're just kind of thinking about the oxidation states, right? For oxygen, just as we said, we ultimately find this equation, and we had 2O at 0 oxidation state to 2 at -2. So that works. Okay, so let's try this again. Okay, sorry. Then let's do the last steps here, which would be, first of all, we need to multiply if we have some difference in the amount of electrons, right? So the oxygen, we had 4 electrons. For the iron, we had just 1 electron change. So we have to multiply the iron equation by 4, or I guess we maybe could divide the oxygen one by 4, in order to make it so that we have the same amount of electrons exchanged, right? So we're going to multiply the iron by 4. So 4 of these Fe2 pluses for 1 change in oxygen, O2. So we take the 4 here, 4 FeOH3 plus 12 H plus 4 electrons, and that's really where we're balancing here at this point. Yields 4 Fe2 plus and 12 water. Then we can subtract one from the other, and here's where we could flip it and add if we wanted to. Really doesn't matter. And we get a net reaction of 4 Fe2 plus 12 water plus oxygen plus 4 protons plus 4 electrons is in equilibrium with 4 iron hydroxides plus 12 H plus 4 electrons and 2 waters. So we'll see the electrons will cancel when we do this. And some few other things will also, and I'm going to move this out of the way a little bit. So this was our kind of second step, third, fourth, and fifth. Okay, so our final reaction then, a little small here, but it's 4 Fe2 plus 1 oxygen plus 10 waters is in equilibrium with 4 FeOH3 and 8 protons. Okay. Make sense? All right. So try again with HOCl this time. here's the first 5 steps for you, kind of summarized. All right, got some progress here. Okay, so for the HOCl, we can put that, we will expect for Cl minus to come off as kind of one of the products. might not have been intuitive to you yet, but you'll see that in a lot of systems. If we do have some reaction with chlorine, usually the Cl is changing oxidation state and is getting kicked off as chloride Cl minus. So free chlorine, then, we have a situation where we stop and think about it. HOCl, the O should be a -2, the H should be a +1, and so to get this to be a charge balance, the Cl should also be +1, according to our oxidation state rules that we talked about last time. So that means if we go from a 1+ for the Cl to a 1-, we've got a change of 2 there. That's sort of driving the net reaction. So to balance on chlorides, we're going to start with the oxidized version of it, so the higher oxidation state. So HOCl is on the left, Cl- is on the right. Balance by adding enough waters, just takes 1. Balance by adding enough H+ to both sides, just takes 1 on the left. Then we have HOCl plus H+ is an equilibrium with Cl- and H2O. At this point, we have a +1 on the left and a -1 on the right, and we're going to add electrons to the side with the higher charge, the higher net charge, like a more positive charge, to balance the other one. So that means we're adding 2 electrons on the left to yield a net -1 charge on the left to match the -1 charge on the right. Okay, and we double check our oxidation state that I kind of started with here. Cl at the 1 state plus 2 electrons will yield Cl on the -1 state. Okay, make sense? For the let's see, for the iron, it's going to be pretty similar to what we did previously. I think the book's just taking exactly from the same one as last time. Essentially, if we flip back, we are taking Fe. It's essentially the same reaction here, right? Fe is going from the 2+ state to this 3+ state with the OH3, FeOH3, and the amount of electrons to do that is the same. Right, so we actually just take that same reaction that we had already solved for and move that forward. Okay, so with that, we need to balance how many electrons do we need to add? Well, we multiply our iron in this case. We had 2 electrons in our chlorine exchange. Now we have to multiply the iron by 2, right? The 2 FeOH, this equation by 2. Okay, then we can combine them since we have a matching 2 electrons on each side, and go from there. Subtract. We will cancel several things out. We end up simplifying to 2 Fe2+ plus 5 waters plus HOCl is in equilibrium with FeOH3 solid plus 5 H+ and 1 chloride. Okay, great. All right, any questions on that? Okay, one more example. We'll do ammonium, NH4+, is released into water in the decomposition of natural organic matter, so cellular material containing proteins in particular, and it's oxidized to nitrate. This doesn't really happen without biological activity necessarily, or not in the meaningful amounts. But bacteria do it pretty well, and we can use a chemical reaction, this redox reaction, to describe it regardless. So we're going to take dissolved oxygen, DO, to oxidize ammonia. So let's work that one in the same manner we did previously. Right? So we can, maybe a good starting point is to just say, write to ourselves, what species do we have? We know we have NH4+. We're going to nitrate, NO3-. We're going to have dissolved oxygen, which is going to be O2. And we're going to, of course, have water. Okay, so those are the known pieces, and we can go through the same processes. So I'll kind of work alongside you here, and look at the book solution. We can actually just take the oxygen one we used last time. Turns out that sometimes these very common reactions are going to be pretty typical. So the oxygen changing oxidation state from O2 to water is always going to be this. All right, so that list of 8 rules kind of feels a little overwhelming when you first take a look at it, one big slide, all this text. But as you start going with it, it kind of becomes a little simpler, right? Balance the big stuff or the key points. Then you go on to oxygen and water, H and H plus, and the electrons, right? This time, let's see about putting it all together. Change the font a little bit. So we should end up getting, so the same one for oxygen, we've got 4 electrons transferring there. And then for the nitrate, NO3 minus, that nitrogen group has to have a very positive charge oxidation state to account for all those oxygens. For the NH4 plus, it's got to be a negative, right, to account for all the positive charges from the H plus. So we can say, even before we even really go there, if each oxygen has a -2 here and we're net -1, this should be a +5. So this should be kind of in the 5 state. And the one over here should be a -3 state, right? Because -3 + 4 is going to be +1. Okay, so yeah, considering that, that should give us, when we balance this, we put the nitrate on the left. Nitrate in balance with ammonia, adding 3 waters to account for the 3 oxygens over here. Once we do that, we have to balance the hydrogens, and we've got 10 on the right, 4 here, and 6 here. That means we need to put 10H plus on the left, and we're left with just that 10H plus and the -1, we're left with a net plus 9 charge on the left, and we need a net +1 charge on the right. So it leaves 8 electrons we need for that reaction. Okay, so we've added 8 electrons there. That means to do our combination, we need to multiply everything here by 2 to give us 2O2 plus 8H plus 8E minus in equilibrium with 4H2O. Then we can subtract these guys. So subtract 2O2. I'm just going to, I'll put a bracket so we're subtracting this whole thing. Okay, once we do that, it should end up looking like NO3 minus plus 2H plus, no electrons. Since I have a negative oxygen value, I'm just going to put that over to the other side and say this is going to be in equilibrium with, well, we will also end up with a negative value for the waters on the right side, so I'm going to add that over here, +1 water in equilibrium with 2 oxygen and our ammonium. Okay, so I think that should be kind of where we end up. Let's double check with how the book does it. Get the same oxygen as we said. Apologize, I kind of wrote over where this is filling in. Let's see. Their final equilibrium they put the nitrate on the right, which I suppose maybe that's, I guess you can get there if you subtract the other way. So ammonium, I guess that's kind of the reaction we're really looking for, is ammonium converting. But okay, at any rate, with 2 oxygens in equilibrium with 2H plus and a water. Okay, so, and the nitrate. So it does balance, but we probably ought to flip it according to how it makes sense to write it compared to what I did, right? So instead of subtracting the NO3 minus term, excuse me, subtracting the, where did I put the, I didn't even, oh, sorry. Yeah, instead of subtracting the oxygen term from the nitrogen term, if we subtract the nitrogen term from the oxygen term, we get it in that way. Or we can just flip it. Anyhow, okay, any questions on that? All right. Okay, so I want to talk a little bit about reduction potentials. So you might see this, or you probably will see this pretty often in the literature, talking about all sorts of different chemical systems, electrochemical systems, everything from biochemistry to advanced photochemistry. When is something going to accept an electron or give an electron? You'll see redox potentials a lot. And really what we're typically referring to when we say redox potential is the reduction potential. And what we're describing here is a lot like the Gibbs free energy, except it's applying to the oxidation, or rather reduction potential, the tendency for that reduction to happen. And this is going to be slightly different than the Gibbs free energy in that it's a potential up until we're like applying it. We'll relate that in a minute, but it doesn't really, it's the stoichiometry of it doesn't matter so much as how much potential does it take to move an electron from here to there. So that's depending on the atomic composition itself, right? Some atoms are going to be really pulling at those electrons, more electronegative, compared to others. So to pull an electron in a given field from one point to another, or I guess the technical term for voltage is to take a test charge, a positive and imaginary positive charge, as if it's like the inverse of an electron, to move it from one place to another in an electrical field, a static electric field. That's the definition of voltage. That's kind of the thing we're talking about, right? To move an electron from one place to another, there's a potential energy there to do that move. So that's voltage. That's how we're going to quantify our the likelihood for this to happen, and to get some thermodynamics and to relate this to thermodynamics to to what extent is that going to happen. So we have a few examples of redox potentials, reduction potentials here. This is going to be the standard E, standard reduction potentials. And we can get this E naught thing of this standard energy for all sorts of half reactions. Now, we can't actually get it for a full reaction because there's two redox reactions happening in one redox reaction, two half reactions. So because we can't measure them independently, we always deal with them together. And to get there, you know, we run into the same problem we had with our equilibrium chemistry. We don't know exactly the energy on one side or the other with two reactants. So, well, how do we do it? We make an arbitrary definition that hydrogen is zero, just like we did with the Gibbs free energy of formation. So with that, the defining H plus one electron in equilibrium with the half of H2, defining that as zero, we can then pair with any other reaction that involves, like we can build from there and find all half reaction values. Because there's a lot that combines with hydrogen, and then anything that combines with that thing that combined with hydrogen we can know, right? So we can solve for everything in reference to a standard hydrogen potential. So you'll see a lot different standard reference potentials. We'll talk more about this next time with different electrochemical cells with an electrode that has some sort of material that we are referencing our measurements to. And we'll see very often these things written as standard hydrogen potentials or electrodes, so as the reference. Okay, so just to take a look at a few examples here, the oxygen one that we were taking a look at with a 4-electron transfer, this is a positive 1.27 volts. The dissolved chlorine gas here, Cl2, this one is a positive 1.39 volts. So before we move anywhere else, we can already see, well, these two are pretty strong oxidants. Chlorine gas we know is a very strong oxidant. Oxygen is obvious as an oxidant. So the higher this number, the stronger the oxidant. Conversely, of course, if it's lower, that's going to be more of a reducing agent. And we have sodium, for example, Na plus electron. This is a very negative one. So we've got some examples on that. Okay. There's a few more we could take a look at for examples. So we can find all sorts of reference redox values out there in literature. And we can take a look specifically here where we're looking at this potential energy, standard potential energy. Next time we will look at this value. It's kind of like PE as obvious. We can also take a look at the equilibrium constants for these as well. All right, so we're going to elaborate on those pieces a little bit. There's a few more on this table that was just cut off onto the next page. So my point here is there are reference tables. We can take a look at these and find highly oxidizing, highly reducing, and everywhere in between. So this standard potential, it's going to apply to standard conditions, and we're going to define those standard conditions as the case when all reactants are at a unity in terms of their activity. So 1 molar if we had dissolved stuff with no activity corrections. Okay, so pretty simple and straightforward there. Of course, we're not including electrons here. That would just be, the book didn't really elaborate. I just don't think we could really give an activity for electrons. So we're just going to ignore that. But basically everything's at unity in terms of their activity. Kind of already talked ahead of myself on this stuff. So we can't measure each one individually. So we set the standard potential for hydrogen at 0. And then we measure the difference in reference to that, and we can get everything else. This electrical potential does not depend on the stoichiometry, which is not true for the Gibbs free energy. And yeah, I actually was ahead of myself. So I said all of this stuff. And I think, yeah, so I've got, because metals tend to be very strong reductants, they will often react very strongly with oxygen and or water. So you might have seen some stuff about metal fires, or what happens if you take elemental sodium and put it with water. There's a strong, violent reaction. So I've got a fun video we'll watch in a minute to be a little more entertaining than I can be. But I think that what I'll do, because I'm not sure about how the YouTube streaming and stuff happens, I'll give good credit to Tom here, start the video and then end my stream. So if you're watching online or later, find that video and watch it yourself. Just don't want to do anything I'm not supposed to with that. So we'll come back to that in about 5 minutes. Want to just kind of cover the rest of the connection between the standard potential energy and Gibbs free energy. So this E naught is a thermodynamic, or kind of relates to the equilibria for these reactions, but it's not necessarily the thing we measure when we take a measurement, right? So we can relate it and even calculate it based on Gibbs free energy stuff. But if we're measuring something to try to find it, we might have to do some corrections, because we're going to use maybe a platinum electrode as a reference, or some other electrode, and then we have to convert that up to the hydrogen reference that our standard applies to. Plus, if we're doing a measurement, maybe we're not at unity for activity, so that would have to correct for that also. Okay, so this standard potential energy relates to our Gibbs free energy of formation, the standard Gibbs free energy, with this equation. We've got delta G naught is equal to NFE in a cell. This is going to be the number of moles of electrons, got the Faraday's constant, and that standard electrical potential in volts. So that's a pretty straightforward relationship. We need the Faraday constant. That's kind of giving us charge per mole, essentially. And we've got values for that, units for that. So all these pieces, relatively easy to put together. And with that, then we can say that since we know from thermodynamics the delta G formation is minus RT natural log K, we can do some derivations and get this in terms of the E instead of, get K in terms of E instead of getting in terms of delta G. So we can rewrite this to say natural log of K is equal to N over RT times this potential energy, log K if we want to convert it from log, and we can simplify it a little further, basically getting it in terms of the standard electrical potential. Okay, we also can relate this standard E versus regular E just in the same way we can do standard Gibbs free energy in relation to Gibbs free energy, right? We talked about that at standard state versus where we happen to be right now. So we can take our equation where we do that with delta G and divide everything by negative N times the Faraday constant, and ultimately simplify and get this guy. So we can get a formulation with E there. Okay, that brings us to the Nernst equation, which is essentially putting these pieces together and we can include a factor that changes from natural log to log. That's this 2.3 business. We also divide that by the Faraday constant. That's where the 0.059 was coming from, where we saw in this equation. So we get the Nernst equation here, and this is for a system with the activity of oxidant divided by the reductant. Now, convention, we typically do products over reactants, but the convention is slightly backwards in this redox chemistry world, where we're going to put the most oxidizing thing on the left and then the reduced form on the right, which kind of flips it a little bit. So if you notice from the last slide, we ended up with a positive here. That's just flipping it so that it makes sense with our convention of doing things as products over reactants. So don't worry too much about that. That's a little detail in the derivation where we get this Nernst equation. Otherwise, it looks quite similar to this, right? So we added the plus here to flip it because we see the reduced and oxidized right there. We're just flipping that. Okay, so the general equation here, get this log of the sum of whatever oxidants over reactants. So there's our Nernst equation, and that's going to relate our standard potential energy to our potential energy as a function of how many electrons we've got going on and the this activity quotient. Okay, so I'm going to play us a video here in just a second. Next time we'll cover cell potentials and look at this PE, so potential energy as a log function, so we can do PE-PC diagrams and PE-PH diagrams. Yeah. Oops. So I think that I meant to have the homework due the day the exam review is. So I'm looking at my calendar here. Today's the 14th. So I'm behind a lecture, basically. That's right. Yeah, okay. All right, so I will say, do your best on that. I want to cover that material, but I'm going to kind of prioritize probably exam review next time. So give it, whatever we didn't cover, do your best shot and recognize I'm not going to put that specific content on the exam unless I end up having time to cover it on Tuesday, which I don't think I will. So that'll be something we'll catch up on after the exam, which will be relevant for your final project, probably, or could be. Okay, so I'll just have to adapt that way. Definitely not going to move the exam, and yeah, do what you can with that. Thanks for the heads up there. Okay, well, since we're not having enough fun yet, here's a video I want to show you. So if you're watching online, the link is there, or you can search this. Let's learn just a bit about lighting metals on fire. Might have to skip a little if we're going to get the whole video, but all right. But I'm going to end the stream there so that